Howdy. We're going to be talking today about the center of mass of a system of objects. The center of mass can be thought of as the balance point. And we're going to use the abbreviation COM for center of mass usually. So the center of mass is the balance point of a system of objects. So for example, if I have some kind of, maybe I have a hammer, and I can think of the hammer as being like this, and here comes the handle, like this. And we can think of the hammer as being a system that includes the head right here, and then the handle right over here. And when I find the center of mass, or the balance point of that system, it turns out it's going to be pretty close to the head, because the head is so much heavier than the handle. So we're going to be talking today just about how to compute the center of mass, and then in class on Monday we'll talk about some of the physics that goes along with that. To get there, I want to take you back to the concept of average. You all know how to average a bunch of numbers. You say something, when I ask people how to average, they say something like, you add up all the numbers and divide by the number, which is a little vague, but it'll do. So if I have a set of numbers x1, x2, x3, all the way out to xn, and I say, give me the average, then you would say that the average is x1 plus x2 plus x3 plus all the way out to xn divided by the total number of numbers. And we're going to give that symbol x bar for x average. This expression here on the top is a little bit long-winded. So very often mathematicians and physicists will roll it up as a sum, so that x bar is the sum of all of the x's, starting at the first x and going out to the nth x, and then we divide by the total number. Well, that's all good, but sometimes we want some of our x's to count more than others, and that leads to the concept of a weighted average. For example, your physics grades are a weighted average. The homeworks count as 15% of your grade, and your labs count as 20% of your grade, and your quizzes count as 25% of your grade, and your tests count as 40%. And we'll just check and make sure that all of the weights should add up to 100%, and sure enough, they do. So when I compute your grades, the way that I compute them is like this. Let's say that you have a 90% on your lab average, which is very good, and you've been doing well on your quizzes. You have an 85%, and you have a 92% on your tests, but you're one of those people that kind of slacks off, so you have a 75% on your homework. Boo, hiss. And so now to compute your total grade, the way that I'm going to do it is like this. I'm going to multiply the weight times the grade, weight times the grade, weight times the grade, and add all those up. And when I multiply the weight times the grade, I get these values. Right here. And we can add up weight times grade. to get 8730 is your total number of weighted points. Now your average is going to be the sum of weight times grade, which we just computed, divided by the total amount of the weights, which is going to be 8730 divided by the total amount of weights is the 100% that we had right here. So that this person has an 87.3 weighted average. And if you take a look back at the grades, that makes a whole lot of sense here. The 75 pulls the average down a little bit, but not very much because it only counts 15% of the grade. So our general weighted average looks a whole lot like the average formula right here, except that instead of dividing by the total number, I divide by the total weight. And instead of adding up just each individual item, I add up each item times its weight. That's the weighted average concept. And this is very general in statistics. And it's going to be the formula that we use for our center of mass. Here it is. The center of mass of a system is the weighted average of all of the positions of the objects with mass as the weight. In other words, if I have a bunch of different objects, 1, 2, and 3, then the center of mass is going to be the average location, but I'm going to count more massive objects with greater weight than less massive objects. So here's our formula that we're going to be using. Center of mass equals the sum from I equals 1 to n of mass times position divided by the sum of all the masses. Notice that this will always, this bottom right here, will always equal the total mass of the system. So I'm going to do 3 examples to show you how this formula works in action. And along the way, we're going to train our intuitions just a little bit. For our first example, we're going to take a man on a seesaw with his young daughter. And so the seesaw is going to be a 10 kilogram seesaw, and it's going to be 4 meters long. And the man is going to be 100 kilograms. And the daughter is going to be 20 kilograms. And so the question is, where is the balance point for all this? If we're going to put a fulcrum underneath the seesaw so that the man and the daughter can balance, where should we put it? Definitely we don't want to put it directly in the center, because the man will go way down, the daughter will go way up. So we want to place the fulcrum at the center of mass for the balance point. To do this, we're going to use a familiar procedure. We're going to pick a reference frame that is an origin and a direction to be positive. And we're going to mark up coordinates. And then we're going to compute the center of mass, which is going to be the sum of mass times position divided by the sum of all the masses. Just like that. So in our particular example, we're going to start by picking an origin. It makes sense to pick the origin on the left so that we can make the direction this way be positive. So there's our reference frame. And now we're going to go through and mark coordinates for each one of our objects. Notice we have 1, 2, 3 objects. We have the girl, we have the seesaw itself, which has mass, and we also have the father. So we're going to have the girl here at 0. The seesaw, the plank here is an extended object. We're going to place its location at its own center of mass, which is right here in the middle, which is at 2. And then the father is all the way at the other end. He's at 4. So if we made a little chart for each mass and each location, we would say the girl is at 0. We would say the seesaw is at 2, and the man is at 4. Technically, I should put my units here, kilograms and meters. However, the kilograms are going to cancel out when we do the computation. And now, the thing that we need for a weighted average is mass times position. So I'm going to compute that for each object. 20 times 0, 10 times 2, and 100 times 4. And we add them up. We add up the total masses, giving 130. We add up the total mass times position, giving 420. And we're ready for our center of mass. Here's our formula. Center of mass is equal to sum of mass times position over sum of mass equals 420 over 130. That's kilogram meters over kilograms. And that gives us, when we do the division, 3.2 meters as the center of mass. Where is that 3.2 meters located? Well, it's located right here. As we suspected, it's much closer to the father than it is to the girl. The father counts more because he weighs more. Now, I want you to notice that the number that we got, 3.2, was dependent upon the reference frame. However, the location, the actual physical location, is independent of the reference frame. To see this, I want you to take a minute to rework this problem, but with a different reference frame. Put 0 in the center of the plank of the seesaw, and rework this problem, finding the center of mass, using the same table format that we did for this. Pause the video at this time, do your computation, and when you come back, then we'll work it through. Welcome back. So hopefully, having picked a 0 right here, you then marked up coordinates. The girl is at -2. The father is at +2. And if we do the same table format that we did before, the girl is at -2 here. So mi times xi is -40. The seesaw is at 0, giving us 0. And the father is at +2, giving us 200. And when we add up, we still have the same sum of masses, which is 130. Now we have 160 as our sum of mi times xi. And the center of mass is sum over sum, or 160 over 130, which turns out to be 1.2 meters. We ended up with a different number for the center of mass, but when we locate that center of mass, here it is, at the same physical location relative to 0 as it was in the first computation, right there. Our center of mass is physically one single unique location, but the number that I get depends upon the reference frame. So that's the first example. The second example is going to be fairly simple. Did you know that technically the moon does not revolve around the Earth? Instead, the moon revolves around the center of mass of the Earth-Moon system. But as we're about to see in this example, the center of mass of the Earth-Moon system is basically just the Earth. And so the point of this second example is this. If one object is overwhelmingly larger, more massive, much more massive than the rest of the system, then the center of mass is at that object. It is the center because it weighs so much more than all the rest. And so to see that, we're going to take a look at the Earth-Moon system and compute the center of mass of the Earth-Moon system. So here we have the Earth and the Moon, and we do a little bit of Googling on the BATnet and discover that the mass of the Earth is 5.98 times 10 to the 24th kilograms, whereas the mass of the Moon is 7.35 times 10 to the 22nd kilograms, or only about 1/100th the mass of the Earth. And we discovered that the average distance from the Earth to the Moon, that's a center-to-center distance, is 384,000 kilometers. And so using this information, we're going to compute the center of mass. Now I'm going to do a couple of things with the numbers to make the computation easier. The first thing is I'm going to rewrite this distance in units that have fewer zeros. So 384,000 kilometers is the same as 384 megameters. And I'm also going to write the masses so that they have the same exponent. 5.98 times 10 to the 24th kilograms is the same as 598 times 10 to the 22nd kilograms. And now my masses have the same exponents, and I can effectively ignore that exponent because it cancels out in the computation. Now we mark up the origin. It makes sense to put our origin here at the center of the Earth. And we have a location. Of course, this guy is going to be 384. That's measured in megameters. And we can say, we can set up our chart. Mass, distance, and mass times distance. The mass of the Earth, 598. Times position of 0 gives us 0. The mass of the Moon, 7.35. Times position, 384. Gives us 2815 as mass times position. Add up the total masses, giving 605. Notice that I round off because the mass of the Earth doesn't have decimal points given here. And the total mass times position is 2815. And now we compute. Center of mass is equal to sum of mass times position, or sum of mass, which gives us 2815. That's going to be times 10 to the 22nd kilogram megameters over 605 times 10 to the 22nd kilograms. I promised you earlier that the times 10 to the 22nds would cancel out, and in fact they do. So that when I actually did this computation, I even left out the times 10 to the 22nd because I knew they would cancel out. And the result that we get is 4.65 megameters as the center of mass of the system. Where is this center of mass physically located? Well, we go back to the BATnet and discover that the radius of the Earth is 6.37 megameters, so that the center of mass that we have here is roughly located right here, 2/3 of the distance from the center out to the Earth's surface. In other words, the center of mass is located inside the Earth itself. So it's not really wrong to say that the Moon revolves around the Earth. It just doesn't revolve around the exact center of the Earth. The Earth, by the way, is also revolving around its center of mass, so that as the Moon goes around it, it pulls the Earth in a very tiny wobbly motion so that it revolves. It does this kind of a thing as the moon goes around it. For our last example, we're going to consider center of mass in 2 dimensions. As you know, location or position is a vector quantity, and so the center of mass is also a vector quantity. In our examples 1 and 2, we were operating in a straight line, so we simply used positive or negative as our way of indicating direction. But let's consider now a 2-dimensional object. I want to consider an object that is made up of a bunch of square tiles. So here's a bunch of square tiles laid out. There, there. And for simplicity, let's assume that each one of these tiles has a side of 1 meter. And now what we want to know is, where is the center of mass? Okay? Notice that one thing that is not given in this problem is the mass of each tile. However, because each tile is exactly the same, we're simply going to take the mass of each tile to be one tile mass. And that will make our computations a little bit simpler. As we did before, we're going to pick an origin, and then we're going to go through and mark up the coordinates for the center of each object. To me, it seems simplest to make the origin be right here at the center of the bottom left object. And that way, I can have each of the locations be integers. And when I do the locations, I'm going to give them in terms of x and y. So this guy is 1 meter. This fellow right here in the center is 1 meter to the right, so he's at 1, 0. This guy is at 2, 0. That puts this guy at 1, 1, 0, 1, 0, 2, 0, 3. And now we're ready to do our chart again. Mass, location, and mass times location. Because we were clever, we made the mass 1, and so that's going to make the computation kind of simple. So we're just going to do one each tile at a time. And I'll check them off as I go so that I don't double count or forget anyone. So there's one tile, and its location is 0, 0. Here's a tile whose location is 1, 0. Tile at 2, 0. We have a tile at 0, 1. We have a tile at 1, 1. Sort of ran out of room there. We have a tile at 0, 2. And we have a last tile here at 0, 3. And now we can do mass times position. Notice that the mass is a scalar, so it simply multiplies by both the components. We have 1 times 0 plus 1 times 0 gives me 0, 0. 1 times 1, 0 is 1, 0. 1 times 2, 0 is 2, 0. 0, 1, 1, 1, 0, 2, and 0, 3. And we're ready to add them all up. The total of our masses is 1, 2, 3, 4, 5, 6, 7. 7 total tiles. And the sum of our mass times positions, we're going to add up the x's and y's separately. So the x's are 0 plus 1 plus 2 is 3, plus 1 is 4. 0, 0, 0, 1, 2, 4, and 7 is the sum of mass times position. And now the center of mass is the sum of mass times position over the sum of mass, which is 4, 7, over 7, which is equal to 4/7. In decimal form, that would be 0.57, comma 1. And if we take a look at where that is physically located, 0.57, comma 1 is going to be over just a little more than a half meter and up 1, so that our center of mass is where we pretty much figured it should be, which is right here. I hope this is helpful to you in terms of computing center of mass. To sum up, pun intended, the center of mass is the sum of mass times position